Good morning, y'all. Today is our last video of Chem 1, so yay. The first thing we're going to talk about in this video is kinetic molecular theory. Then we're going to talk about some gas stoichiometry, and then we'll go into real gases, and then that'll be it. So, about kinetic molecular theory. This is the simplest model for the behavior of gases, and it's got several different postulates. You will need to know them, but the gas is modeled as a collection of particles, either molecules or atoms, depending on which gas, and they're always in constant motion. So these are the four postulates. You do need to know them. First one is particles of a gas are constantly moving. Also, it's random motion. Okay. The attraction between the particles is negligible. So that's just saying the particles are not attracted to one another. They're just moving. And when they hit each other, they bounce off, they don't stick, and they keep moving in a different direction. That's the third one. And then the last one is that there's a lot of empty space between gas particles compared to the size of the particles. It is important to note that the average kinetic energy is directly proportional to the temperature in Kelvin. So as you raise the temperature, the speed of the particles increases, or the kinetic energy, but they're not all moving at the same time or at the same speed. It's about the average kinetic energy. Okay, just remember, we talked about this at the beginning. Pressure is force divided by area, but that's not how we are going to calculate force or pressure. We don't really do it with that equation at all. That's really a physics equation. But you just need to know that pressure is the particles hitting the walls of the container. Okay, so here they're hitting the walls of that container to show the different pressure. All right, as for the velocities, I'm not going to ask you to do any of these calculations. I do need you to know that gases in the same container that have the same temperature will have the same average kinetic energy or the same speed. Okay. Okay. If they have those different masses, for them to have the same kinetic energy, their velocities have to be different because mass is part of the, if you remember the basic, it's 1/2 mv squared from physics. So that mass is important. So a larger mass to have the same kinetic energy would have a smaller velocity. And a really small mass to have the same kinetic energy would have a faster velocity. So this graph here is called a Maxwell-Boltzmann distribution graph. You're going to see more of them in Chem 2, but it's just saying to have the same average kinetic energy, which all of these do, heavier molecules have to have a slower speed. So if we look here, this one is the fastest speed overall because it could be from 0 to 35,000 meters per second. Oxygen, on the other hand, pitters out about, 1,250 meters per second. So the lighter ones will move faster. The heavy ones will move slower. The heavy ones are always going to be at this beginning part of the graph because they peak pretty early and then they're done. And as your temperature increases, so will your average velocity. So here we've got different, this is also the same type of graph, but instead of showing the same temperature, this one's showing different temperatures. And you can see the lowest temperature has the first peak. It doesn't go as fast, but this 2000 Kelvin goes much faster over the period of time on average than the 273 Kelvin. And some of you, we've seen more of these graphs now because of COVID. Okay, so there is this root mean square velocity question. If you would like to go through it, you're more than welcome to, but there's not going to be any on the test or quiz. The next thing is the mean free path. This just says that molecules of gas travel in straight lines until they hit another molecule or their container and then they bounce off. Okay, so that distance that the molecule travels between collisions is called the mean free path. And that path decreases as your pressure increases because then they're hitting the walls more frequently. What I need you to know for this slide, again, this one has calculations as well, but we're not going to have calculations yet. I just need you to know the difference between diffusion and effusion. Diffusion is the process of a collection of molecules spreading from high concentration to low concentration. Okay, so this is like osmosis. Lots of you know about osmosis. It's always from high to low concentration. That's a normal diffusion. Effusion is something different. That's when they traveled through a small hole into a vacuum, which means there was nothing on the other side. So here we've got the small hole, and some of them are coming through the hole. It is important to note that heavier molecules will effuse more slowly than slower molecules. The reason being is because those heavy molecules are moving slower, even though the average kinetic energy is the same in the whole container. So it's less likely they're going to make it through the hole. Again, we're not going to do this calculation at all. So again, if you want to go back and check the PowerPoint, you're more than welcome to, but it's not going to be tested. What will be tested are stoichiometry with gas laws, and particularly the ideal gas law. Both of these equations here are a rearrangement of the ideal gas law. Just also remember that at STP, 1 mole is equal to 22.4 liters. So if you're asked for volume, you can go that route. Okay, so our normal planned route when we do stoichiometry is mass to mass. That's that first image. But we could go from pressure to pressure, pressure to volume, any of those things. The key here is that we're changing compounds in the middle, and we still need this mole ratio. Very important. The mole ratio has to be involved in stoichiometry. So let's look. Here we've got, I want to know the volume of hydrogen gas. So I'm going to do V of that. Okay, and it gives us a temperature, a pressure, and it gives us mass of methanol. So we're over here. Okay, so what we need to do is, so the temperature and pressure are of the hydrogen gas. The methanol, well, that's not what we're dealing with. So we're going to start with our 35.7 grams and convert that to moles. Then we use our mole ratio. Then this moles goes into our equation so we can solve the volume of hydrogen. You really have to pay attention to what it's specifically asking. Okay, so this specific problem is a little different. It works the other direction. So first, we're going to do the ideal gas law. The key is you need to know what goes together and how to use it. So all of this is of oxygen. Of course, I'm not writing. Okay, and then it wants to know how many grams. So first, let's do our PV equals nRT to find moles. So N is equal to PV over RT. Yes. So I've got, don't forget, pressures have to be in atmospheres. So I've got 0.980 atmospheres times 4.58 liters divided by 0.0821. Kelvin. I get 0.178 moles of O2. So then we do our stoichiometry. So I've got 0.178 moles, O2. 1 mole of O2 is in our problem. We want to go to silver oxide. And then we need the mass of silver oxide. And I get 231.74. Okay. And I get 82.3 grams. I'm going to write that up here. All right, so it's got another problem. What mass of Ag2O in grams is required to form? And then we've got other values, new ones. But we're still trying to find moles. And since it still wants mass, all I'm going to do is I'm going to delete this number because that's the only thing that's going to change. So my pressure now is, don't forget to convert to atmospheres, so 734 divided by 760 is 0.966 atmospheres. Times, remember this needs to be in liters, so it's 0.388. Okay, and I've got 298 Kelvin, because that's got to be in Kelvin. And then I've got 0.0821 liter atmospheres per mole Kelvin. Okay, I get 0.0153 moles of oxygen. All right, so then we just do the math. And my new value is 7.10 grams. Okay, so just make sure you're paying attention to what they're asking for. All right, now we're using molar volumes for this. So the only volume I have here is this 1.24 liters. That's the only given I have. That's of hydrogen. So I can get to moles because I know that there's 22.4 liters in 1 mole. So then we do our mole ratio. 2 moles of H2 is 2 moles of water. And then 1 mole of water, 1 grams of water is 18.02. And I get 0.998 grams of water. Okay, here's another one. This one's going the other way, so let's just do that one. Got 10.5 grams of water. We know that the molar mass of water is 18.02. Then we do our mole ratio. I've got 2 moles of water to every 1 mole of oxygen. And then oxygen's mass is 32 grams. Oh, but it doesn't want grams. It wants liters. So then that 22.4 liters of oxygen gas. All right, so let's do our math. 10.5, 18.02. I get 6.53 liters of O2. So just keep in mind, if it says at STP, then you can just say that a mole is equal to 22.4 liters, and we keep it moving. All right, so just some properties of gas, a review. Remember, gases will expand to fill their container, and we talked about that in chapter 1. Also, they take the shape of their container. They also have a low density, so they're going to be higher in the atmosphere than things like solid or liquids. Also, they're compressible. You can squish them. And then mixtures of gases are always homogeneous, which is like air is a mixture of gas. Okay, real gases, on the other hand, do not behave like these ideal gases, but they don't behave that way at those high temperatures or low pressures. So for ideal gases, we assume there's no attraction between molecules. and the molecules don't take up space. But at low temperatures and high pressures, these are invalid assumptions. So at low pressures, the molar volume is nearly identical to that of an ideal gas. Okay, so it mimics that ideal gas at low pressures. But as the pressure increases, the molar volume becomes greater than an ideal gas. So here, it is not very much deviation, which is why we assume the whole time that ideal gases are what we're doing. Okay, you can see the slight deviation there. And then at high pressures, at high temperatures, the pressure of gas is nearly identical. But at lower temperatures, the pressure is less than that of ideal gases. Okay, and here's also a plot. Notice the ideal gas is flat at 1, but they're very kind of all over the place. And that's it. Y'all have a great day.